Good morning, everybody. Welcome into this third session of the module about molecular evolution and phylogenetics. I see I keep on moving you from my workplace, my office, to my home. We're back at my place. I hope you enjoy the little trips. Today we're going to talk about the complexity of the search space when we are looking for the best phylogenetic tree. And we're going to see distance matrix methods for tree inference and maximum parsimony methods, also for tree inference. The learning objectives are stated on this slide. Understand the complexity of the space of all phylogenetic trees on N taxa. Understand what are the distance matrix methods for phylogenetic inference, and understand maximum parsimony. Yes, next slide. Learning outcomes, to be able to give reasonable estimates of the number of trees on N taxa, be able to build the UPGMA3. This is one distance matrix method that we're going to see a little bit more in detail, and to be able to calculate most parsimonious history on a given labeled tree. Parsimony is usually written with a C, but sometimes with an S, or it's my mistake. So, first, as an introduction, let's see what are the different kind of strategies one can adopt in the quest for the best phylogenetic tree, knowing that also this will depend on what kind of definition we give to this idea of the best phylogenetic tree. So remember the tree inference problem. The key problem in phylogenetics is knowing a series of aligned characters. Here we chose to use as an example nucleotides. Knowing these series of four aligned sites, what is the best tree? Okay, you know that a tree is an acyclic connex graph, but you have many different acyclic connex graphs that you can build, whose leaves would be the four taxa. Okay, here I gave only two examples, but we have many more, as we're going to see in a short while. So the phylogenetic inference problem is to decide which tree is the most accurate representation according to a certain belief, meaning according to a certain evolutionary model, which tree is the most accurate representation of the reality of the evolutionary process that has linked through time these four taxa to a common ancestor. Here the root of these rooted phylogenies. Okay, so what is the most probably correct? Remember that all the models we're dealing with are stochastic models, probabilistic models, so we will never be able to have any certainty about the fact that such a tree is or corresponds to the reality of the evolutionary process at work through the centuries and millenniums. So it's always going to be a probably correct tree that we're going to infer. But which one? That's the tree inference problem. There are many trees one can build on a fixed set of taxa. Okay, so if I set three taxa, I set the set of or the cardinality of the set of taxa to, let's say, n, and if I set n is equal to 3, I must count how many unrooted binary tree topologies do you have with three taxa. There is only one unrooted tree topology. Okay, remember, unrooted tree topologies don't singularize one node that would have only two descendants and no father. we're going to talk in this slide about binary tree topologies, okay? So in a binary tree, all internal nodes have 3 neighbors, and external nodes, or the leaves, have only 1 neighbor. If you respect this, these rules concerning nodes in a tree, and if you respect the rule that the tree must be a connex component, meaning that you cannot have just one taxa or set of taxas totally separated with no path linking them to some other nodes. So if you also stick to the rule of the connexity and the rule of acyclicity, you don't want to have cycles. So for instance, if you had an A here, B here, C here, and C connected to A back with a loop, this would not be a tree because it contains a cycle. Okay. So, sticking to the rules of how to form a tree and the characteristics of a tree being an acyclic connex graph, if you have only 3 leaves, if you want to make a binary tree unrooted, then you have only 1 topology. So we are talking about topologies. This topology A, B, C is exactly the same topology as if you would rotate, or if you would put the B here instead of the A, and the A here instead of the C, and the C here instead of the B, okay? Topology is seen without any idea of orientation. If we add one taxon, and we want to keep the tree a binary one, then we see we have 3 possible topologies. In terms of shape of the tree, it will be the same shape, okay? By the way, we are talking about topologies here, so we ignore the branch length, okay? We're not talking about the branch length. Of course, there is an infinity of different binary tree topologies with 3 taxa, or binary trees with 3 taxa, if you take into account the branch length, because the branch length, in essence, are continuous values taking or variables taking their values in a continuous set, the set of all positive real numbers. So, of course, if you include the idea of branch length, then there is an infinity of trees. But without considering the branch length, saying that this tree is the same as if I had drawn B there and a long branch from this node to B, then you have only 3 topologies, only 1 topology, with 3 taxa, and 3 topologies with 4 taxa, okay? So these 3 topologies are represented here. They differ, they are different, and to make sure about that, you can consider that every taxon has only 1 closest neighbor. The closest neighbor of one taxon is linked to that taxon with 2 edges. Okay, so here, for instance, if I want to go from B to D, I can go with 2 edges. D is my closest neighbor if I'm B. And it's different for me to go to A or to go to C. Okay, there's only 1 path linking any 2 taxa, because we are in a tree, and so there is no ambiguity. But this 1 path linking B to A, for instance, uses 1, 2, 3 edges. Okay, to link B to C, I use 1, 2, 3 edges also. But to link B to D, I use 2 edges. So there is no ambiguity in defining for each taxon, who is its closest neighbor. It's the one linked with 2 edges to that one. Okay, in the context of these phylogenies or topologies with 4 taxa. So if you consider the closest neighbor of A, the nearest neighbor for A, then you have only 3 choices, because you have 4 taxa A, B, C, D. The closest neighbor of A can be only B, that's this case, or C, that's the case of this tree, or D. Closest neighbor of A is D here, okay? So this must be enough to convince you that I'm not lying to you, and that indeed there are only 3 different topologies linking 3 different binary tree topologies linking these 4 taxa. Okay, because once you have determined who is the closest neighbor of, let's say, A, then the rest of the tree topology is determined. A, B, C, D is the same topology as if you had written A, B, and then D here and C here. Okay, it's just a rotation around this point, and the rotation around the vertex doesn't change the topology. You still have 1, 2, 3. You would still have 1, 2, 3 edges to link A to C, 1, 2, 3 edges to link A to D, and similarly for B to C and B to D. Okay, so it's the same topology. Okay, we have 3 unrooted binary tree topologies with 4 taxa, and they are shown here. Now, if you think 1 second with me about how to build a phylogeny with 5 taxa, okay? Any phylogeny with 5 taxa, let's say we name our taxa A, B, C, D, and E. Take that phylogeny that we've not built yet, and imagine that you prune E. Pruning in a tree a taxon is a very simple operation. It consists in removing the terminal node corresponding to that taxon and removing the edge linking this taxon to the rest of the tree. And then you have to merge the 2 branches that were the 2 branches adjacent to the node that you just removed. Maybe I could show this. Let's say, for instance, here, if I want to prune B, pruning B in this graph would be removing this node here, so removing also this branch, and then merging these 2 branches, this one and this one, into one, okay? Because since we have removed B here, this node becomes a node with 1 and 2 adjacent branches, and it is not possible to have a node with 2 adjacent branches in a binary tree, okay? So you have to merge these 2. There is no longer any reason, once you have removed B, to keep as separate branches this one and this one, right? So once you have pruned B, you are left with the phylogeny that links A, C, and D, and that is the only binary phylogeny, binary tree topology, linking A, C, and D. And similar to here, okay? In fact, we can show very easily that if you prune D in this first tree topology, you get the same result, meaning this tree, as if you prune D in this tree topology or in this tree topology, okay? You will have ultimately the same tree topology as this one. In other terms, it's easy to build a phylogeny with 3 taxa from a phylogeny with 4 taxa, where you prune one of the taxa, okay? And similarly, to build these 3 phylogenies, in fact, what we have done is grafting a new taxon D on this phylogeny. And when you graft a taxon, you cannot graft it directly onto an existing node, because then you would have, if I graft D here, a branch leading to D here, my tree is no longer a binary tree, because here I would have a node with 4 neighbors, right? So when I want to graft a new taxon on this phylogeny, I must graft it somewhere in on this branch, or somewhere on this branch, on somewhere on this branch. And you can figure out with a pen and a piece of paper that grafting D here, for instance, grafting D on this branch leads to a phylogeny where B is the closest neighbor of D, and that's this one. Grafting D on this branch leads to the phylogeny or tree topology where A is the closest neighbor to D, that would be here, and it's this phylogeny, A closest neighbor to D. Okay, and finally, grafting D, choosing to graft D on this branch, gives you a phylogeny where C and D are closest neighbors, and it's the first phylogeny. Okay, so it's very easy to build phylogenies with an increasing number of taxa from phylogenies. It's easy to build all the possible phylogenies with n taxa from all the possible phylogenies with n-1 taxa. Okay, so we'll get to this formula very, very soon, seeing that if you want to count how many tree topologies with 5 taxa, it's grafting a new taxon E, and you have 3 choices. You have the choice of grafting it in this phylogeny or in this one. Each of these phylogenies have 1, 2, 3, 4, 5 branches on which to graft E. Okay, so here you have 5 choices to graft your E taxon. Here you also have 5 choices, and here you have 5 choices. Because these phylogenies are already different, none of these different graftings will lead to the same phylogeny. So it's easy to see that you have 3 times 5 phylogenies, or 3 topologies, sorry, with 5 taxa. Okay? You could easily also draw all of them on a piece of paper. It's just that I didn't have enough space on my slide. Okay, so you can choose to graft your E here, or here, or here, or here, or there, and similarly 5 choices here, 5 choices here. So we have 15 unrooted binary tree topologies with 5 taxa. Okay, and this gets us to this formula. How many unrooted binary tree topologies with n taxa? We had 3, and then here you have 3 choices to graft we had 1 phylogeny, you multiply by 3 to have the number of phylogenies or tree topologies with 4 taxa. To have the number of phylogenies or tree topologies with 5 taxa, you would multiply this by 5, etc., etc. Okay? Each time you multiply by the number, you multiply the number of tree topologies with n-1 taxa by the number of edges you find in an unrooted tree of built on n-1 taxa. Okay, and remember earlier I told you about in the previous session about how many edges we have in an unrooted tree topology, and it's 2n minus 3. Okay, so here 2n minus 3, it's 2 times 3 minus 3, it's 3. Here for this 4 taxa, 2 times n is 8, minus 3 is 5, and indeed you have 5 edges here. So with this, from this we established this formula that gives you the number of unrooted binary tree topologies with n taxa. Okay, it's it's a semi-factorial instead of being the factorial, meaning the product of all integers from 1 to 2n minus 5. It's the product of the odd integers between 1 and 2n minus 5. Okay, so 3 times 5 times 7 times 9, etc., times 2n minus 5. And rooted binary tree topologies with n taxa. Rooted binary tree topologies are more numerous, okay? Because from this single one unrooted tree topology. To build a rooted tree topology, you have to decide simply on where do you want to put your root and artificially break this edge into two, and not adding another branch, but here artificially by creating a node that will be the root and that has only two descendants and no ancestor, you create a rooted tree topology from an unrooted tree topology. So you see that in this case, it's easy to see you have three choices to put your root, as many as branches in this tree. And so you have three rooted tree topologies with three taxa, binary tree topologies with three taxa, etc. Okay, so you multiply this number of unrooted binary tree topologies by the number of branches you find in these unrooted tree topologies, and with n taxa, and it's 2n minus 3. Okay, so that's what we have for the number of rooted binary tree topologies with n taxa. This is a large number. Okay, we're going to have numbers, figures in this slide. For n is equal to 10 taxa, we have approximately 2 million unrooted binary tree topologies. For 20 taxa, we have 2 times 2 times 10 to the power 20 unrooted binary tree topologies. Okay, so only the number of possible trees, without even considering different branch length, but only the number of possible topologies, is that huge. Okay, extra information will be in the branch length. Okay, so looking for the right tree is searching an infinite space. It's an infinite space. It's already very large, but not infinite when you consider only the tree topologies. But if you add the fact that you have for any unrooted tree based on n taxa, unrooted binary tree based on n taxa, you also have a set to determine, a set of 2n minus 3 branch length. And this branch length all take their values into the set of positive real numbers, which is infinite. Okay, so that's why I say the space of all trees plus tree topologies on n taxa is an infinite space. So definitely you see that one has to devise strategies, either exact algorithms or including some amount of guessing, rule of thumb, to try and perform a search, taking chances to miss the best tree, but accelerating the speed of the search, because you know that in any case it's not computationally possible to explore an infinite space in a finite amount of computational time. So yeah, tree inference, the problem of tree inference at its core contains this deep problem of finding an optimal. Whatever is your definition of an optimal, you know that you will have to find this out of a space that is infinite. Let's have a break here, not for the videos not to be too long.